Right, so let us get started. So it's a pleasure to have Maine Christos. We're visiting us virtually from Harvard to tell us about a model of D-wave superconductivity, antiferromagnetism, and charge order, inspired, of course, by the problem of cuprates. So Maine is a graduate student working with Subir Sachdev, and yeah, we're looking forward to the talk.
Yeah, so thank you for the introduction and also for the invitation. I'm excited to talk today about some recent work from our group. So like Debanjan said, the title of my talk is A Model of D-Wave Superconductivity, Antiferromagnetism, and Charge Order on the Square Lattice. Sorry, I'm having a hard time. Oh, there we go. Yeah, but before getting into that, I want to acknowledge my collaborators. So Zhuxi Lo is a postdoc at Harvard. Previously, she was at UCSB, but she's been at Harvard since the fall. Henry Shackleton is another grad student in Subir's group. He's been at Flatiron doing a research internship this semester, but he'll be returning soon. And a lot of the work that I'll be talking about today on the student postdoc side was done in very close collaboration with both Zhuxi and Henry. We also gained a lot of insight from Yahui Zhang, who's currently a professor at Johns Hopkins University, and Matthias Scheuer, a professor at the University of Innsbruck in Austria. And then, of course, the work that I'll be talking about was led by my advisor, Subir Sachdev. And if you're interested in any of the topics of this talk, please check out our preprint with the link below here. So the motivation of this project, or the inspiration, was loosely the experimental phase diagram of the cuprates. So I probably don't have to say that the cuprates have a very rich phase diagram. So just to give a brief summary, at low doping, we know that we have, well, a zero doping and antiferromagnetic insulator, which then disappears after some whole doping around p equals 0.05. And then in higher temperature, if we keep whole doping, we end up in the pseudogap phase, which is characterized by a Fermi surface, which is much smaller than you would expect, just given the number of actual electrons in the system. And if you lower the temperature starting from the pseudogap phase, then what you'll find is either the famous D-wave superconductor at low temperatures, or possibly some charge-ordered state, which might compete with superconductivity. And something that'll be very relevant for this talk that I want to point out is that the TC for charge order and superconductivity are relatively similar, and this is a little bit unexpected, given if we were just thinking about instabilities in Fermi liquid theory from two completely separate mechanisms, we might expect that their TCs have no reason to be so similar. So this is a little bit of a coincidence or I guess it's a coincidence if you kind of think about these orders in Fermi liquid theory, but as we'll see, there will be a natural explanation from this from a theory of the pseudogap at low temperatures. And then if you were to keep doping, you would find the pseudogap phase will end, and then coming up above the superconductor in this quantum critical region is the strange metal phase, which will not so much be the focus of this talk. And then if you keep doping, you end up in a more conventional Fermi liquid, where both transport properties and properties of the Fermi surface are expected from usual Fermi liquid theory. So the sort of strategy that we took is we want to describe not only the pseudogap phase, but also instabilities of a given theory of the pseudogap phase to both charge order and superconductivity at lower temperatures. And we want to do this in a way that maybe we can have a chance of sort of explaining this experimental puzzle of why the TCs seem to be so similar and why these two phases might even seem to be competing. And what we'll find is that in our particular theory of the pseudogap is that these different types of symmetry breaking will be related very naturally by a quantum critical point, which I'll get to later in the talk. But first, I want to talk about some of the experimental phenomenology of the pseudogap phase, just to recap some of the features that we want to capture with our theory. So kind of at a very high level, we know that there's some kind of sharp phase transition around whole doping p equals 0.2. You can see this in some thermodynamic quantities. So for example, heat capacity, that there's a very sharp peak, even discontinuity. So something very drastic is happening where the density of states is having some kind of very sharp transition, and the Fermi surface, this is an indication that there's a drastic change in the Fermi surface around p equals 0.2. Kind of resolving what's actually happening further, you can look at something like Hall density measurements, where if you start on the overdoped side at a higher Hall doping P, you measure a Hall number consistent with charge carriers 1 plus P. And then if you keep taking holes out of the system, so going to lower Hall doping, what you'll find is around the same critical doping, the number of charge carriers in the system you measure drops from 1 plus P to P, which is something unexpected from the point of view of normal Fermi liquid theory. And then maybe the most illuminating sort of feature of the pseudogap phase are these famous Fermi arcs. So if we're on the overdoped side at a doping greater than P roughly 0.25, and we're looking at the nodal region of the Brillouin zone, then we see, typical Fermi surface. But in the pseudogap phase, we see these sort of Fermi arcs where it looks like either the Fermi surface is terminating before the antinodal region, or possibly there's a pocket or a very weak electron spectral weight on the backside here. And to kind of give more credibility to the possibility that maybe these are actually describing something like hole-like pockets on the Fermi surface, some more recent ARPES data in very, very clean cuprate samples. So somehow they layer the cuprates in a way such that these layers in the middle have a very, very low disorder. And ARPES in such samples, you can kind of see that the Fermi arc doesn't actually terminate. It looks almost like maybe there's some very weak spectral weight indicating that this is actually a pocket. So kind of to summarize, in the pseudogap phase, we have a small Fermi surface, smaller than we would expect, given the number of electrons in the system. And then we also have this very famous theorem in condensed matter, Lenger's theorem, which tells us at zero temperature, if the Fermi surface is not proportional to the particle number, then one of two things has to be true. We either have to have translational symmetry breaking, or there has to be some kind of topological order in the Hamiltonian, which is describing this whole system. So our approach will be to assume that the pseudogap phase, which is measured at finite temperature, can adiabatically be connected to a phase at t equals 0, which has topological order. And this will allow us to work with a very concrete theory for the pseudogap, on top of which we can then consider instabilities. And then just as a reminder of the instabilities that we're interested in considering, we want to start at a high temperature or a higher temperature description of the pseudogap phase, and then consider at lower temperatures, confining to either D-wave superconductivity or some kind of charge order. And the type of charge order we're most interested in, given experiments, are stripe states. So I think the most prominent sort of stripe state is these period 4 stripe states, which have some additional spin ordering on top of this. Our theory will not be considering spin order, we'll only be considering charge order, but we'll show that we can capture stripe states basically up to period 4 as well. Okay. And so then I'll get into the model that we're considering for the pseudogap phase. So the sort of spin liquid we want to be allowed to have these small Fermi pockets will be the π-flux spin liquid state. So this is a very sort of famous ground state, which I believe was first sort of discovered in the context of large n saddle points of Heisenberg Hamiltonian. And to be explicit, this is a gauge that we're choosing to use. So psi here is a Nambu spinner, which is containing fermionic spinons. EIJ are the hoppings, which guarantee that we'll have π-flux if we move around a single plaquette. So in this gauge, on alternating x links, the y hoppings have different signs. And this I is here to make this whole thing invariant under SU2 spin rotations on top of this SU2 gauge symmetry in the Nambu basis. And then this UIJ is a gauge field, which in general can fluctuate, but we'll be choosing for most of this work to work at the saddle point where UIJ is just equal to the identity. And so just to give some motivation, so why did we choose to work with this particular spin liquid? So maybe to start off with, to give some I don't know, motivation for why this over something else is the only thing we need is some kind of spin liquid with topological order. And we could have chosen maybe like the staggered flux, like a U1 spin liquid or a Z2 spin liquid. So there's kind of some motivation from studies of antiferromagnets on the square lattice, both from experiment and theory, which find sort of indications of spinons associated with this π-flux state near the breakdown of antiferromagnetism in either of these two works. So maybe given kind of the role that Néel order plays in both the cuprate space diagram at zero doping and also fluctuations of the Néel order and superconductivity, this is sort of a motivating reason to consider this over another spin liquid. But what we'll find as we keep going is that sort of the choice of this choosing our spin liquid to be the π-flux spin liquid will basically lead us to, when we consider confining phases, to having additional confining phases than if we picked a spin liquid, say like a U1 spin liquid, which we'll see in a few slides. Yeah, and please, yeah, ask questions. So this is, so having listed what our fermionic spinon sector is doing, now we want to couple the spinons to the physical electrons. So here, psi is still the Nambu spinor, which contains the fermionic spinons. B is the chargon, which is going to couple the spinons to the physical electrons. It'll be spin singlet, but charged under U1 electromagnetism. And then we also have physical electrons, which are also contained in their own Nambu spinor. And this is the way the different symmetries act on this chargon field. In the way we've written it with Nambu spinors, it's easiest to see the sort of gauge SU2 symmetry, but if we expanded it out, it would be more explicit to see the spin SU2 symmetry. And something I want to point out is sort of the similarity of the theory here to sort of older theory works. So this work in particular considered fractionalizing the electron into a bosonic chargon and a spinon. And although we're kind of considering slightly a different starting point approach of electrons coupled to spinons via this chargon in terms of sort of a field content, there isn't much of a difference, but one of the crucial differences will be the fact that we're assuming a π-flux spin liquid, and these spinons move in π-flux versus they were considering a U1 staggered flux spin liquid. And so yeah.
I just asked a question. Maybe you'll get to it. So right now the F's are at a filling of 1 per site, and the C filling will be delta, where delta is the dope hole density, I presume.
Yeah, so most of what I'll be talking about will be a half filling. But yeah, so in our case, the electrons carry the actual charge or the doping, yeah. Right.
Are you going to tell us something about finite delta, or you're only going to restrict yourself to delta equals 0?
I mean, I'm going to tell, like the critical point that I'll be discussing will be a half filling at delta equals 0. The phases that I'll be discussing, like there's no reason why they would die when you add some finite doping. So that'll be general to basically any doping.
Right. So are you going to get to the superconductivity itself at finite delta? Then I'll ask my question later.
Like I guess like in our approach, there isn't much of a difference once you're in the superconductor phase of the superconductor at 0 doping versus finite doping.
No, but there is a phenomenological question that I want to ask, which is that in this picture, at finite delta, if you get a superconductor, meaning if you condense the B's and get a superconducting state on top of that, how many nodal quasi-particles do you get? I think you would get 12 instead of 4.
So yeah, so I guess like we checked this a long time ago. It's not in this current paper. My memory was that you did end up with 12, but we were computing it in sort of a more microscopic model than this. So it was like in the ancilla formalism. Yeah.
Okay.
But I don't want to comment too much beyond that because yeah, we didn't compute it for the π-flux spin liquid, which could make a difference.
Not really, right? Because, but okay, we can talk about that separately. Okay.
Okay. Yeah, so one of the important parts of this sort of theory is that because the fermionic spinons move in a background of π-flux, and because they're coupled this way to the physical electrons, this means that the chargons also have to move in a background of π-flux to keep the physical electrons gauge invariant. And this will turn out to have some important consequences in terms of the possible orders you can get. So starting with the sort of PSG, or the PSG for the fermionic spinons, we can basically read this off from this other work, which worked this all out in the gauge that we're using. And then the PSG for the chargons is similarly easy to read off just from how they should work from this coupling here. And then an important consequence of the π-flux background for the chargons is that because translations in the x and y direction don't commute, this guarantees us that for any minima in this band structure, we're guaranteed 2 degenerate minima. And so this means the low energy theory for the chargons, the degrees of freedom that are important can be expanded about 2 points. So in the low energy theory, we have 2 relativistic bosons. And the fact that we have 2 rather than 1 will be a detail which turns out to lead to the possibility for charge order and a larger symmetry group, which will relate the symmetry breaking orders once B is condensed. And so before kind of talking about what happens when we condense the chargon, I want to maybe have or discuss as kind of an aside how you could have gotten a similar theory from a more microscopic model. So this model is the Ancilla model, which was proposed by Yaofei Zhang and Subir a few years ago. Basically, what it is electrons which are condo coupled to a layer of spins at each site, which are then coupled to a second layer, also via condo coupling, to a second layer of spins via these couplings JK and JPER. And then to see how you can get the theory I was sort of just discussing from a model like this, you could imagine writing each spin in terms of 2 different sets of spinons with the 1 spinon per site constraint. And then again, working in an ambu basis. And then what you'll find if you do the mean field decoupling of all of these condo couplings is that you could have basically a boson relating the physical electrons with the first layer of spinons, and then the analog of our charge on B, which is relating the first layer of spinons to the second layer of spinons. And the idea of this model is that it's very easy to reproduce some of the phases in the cuprates phase diagram. So for example, for the Fermi liquid, if we set this coupling between the physical electrons to the first layer of spins to 0, then the electrons don't see either of the layers of the spinons, and we just have a conventional Fermi liquid. And this is shown if you plot anything like a spectral function as just free electrons. However, for the pseudogap phase, you could imagine condensing the boson, which couples the layer of electrons to the first layer of spinons. And the second layer, which is decoupled, would then be the state, which is in some kind of spin liquid state. So in our case, in the π-flux spin liquid state. And what this previous work found is that you can very easily or match photoemission data in the pseudogap regime very well by assuming some theory like this and basically just fitting sort of hopping parameters to experiments. So this is an example of how you can have Fermi arcs with a very weak spectral weight backside if you are couple the layers like this. And then there's kind of the scenario that we want to consider, which will correspond to when phi is condensed, so we're already starting in the pseudogap phase, and then we want to consider condensing B, which will lead to charge order superconductivity, depending on how B is condensed. So this is sort of just an aside to say that the theory that I was talking about a few slides ago can be derived from a more microscopic model, which is in turn derived from some limit of the Hubbard model as maybe more motivation.
Can I ask a question?
Mm-hmm.
Do you mind going back one slide? I just want to first understand maybe previous page.
Here.
Sorry, yeah. So let me make sure that I understand. So the size C is the electron operator, is that right?
Yeah.
So in spirit, this model is still similar to the model with the ancillas, like the degrees of freedom associated with psi and B are really there.
Yeah. So you could imagine in like sort of the ancilla formalism, like integrating out the second layer of spinons and ending up with couplings sort of like these, or ending up with couplings like yeah.
I see. So naively, it has more degrees of freedom than a simple Hubbard model. It still have that feature in it.
What has more degrees of freedom than a Hubbard model?
Just like the ancilla model, you have extra spins, which is called qubit, whatever, right? So
yeah.
Just if I go back to the microscopics, it does have more degrees of freedom than the Hubbard model.
Yeah. So I guess so. The idea of how you kind of get this from the Hubbard model is you decouple the interaction piece of the Hubbard model with a Hubbard Stratonitous field, which ends up being corresponding to like the paramagnon. And then after sort of restricting yourself to the low angular momentum modes of that field, you end up with something like this.
No, I think I think what Charming is asking is, so you're writing down these C's.
Mm-hmm.
These are, let's say if you wanted to capture a single band Hubbard in terms of the C's, you are adding some additional degrees of freedom, which are your ancilla qubits. So it does have an enlarged Hilbert space than what you might have started out with if you were just trying to describe a single band Hubbard model. Right?
I think like the two layers of spins come from decoupling the interaction in the original Hubbard model. And you could go back to the Hubbard model from here by doing, I think, some kind of Schrieffer-Wolff transformation to integrate out the spins. I guess your comment is about like degrees of freedom in the Hilbert space, right?
Yeah, so for example, somebody run DMRG, do they have to include C, S1, S2 to realize this, given all the ideal interaction that you want? Or one can just literally go with one spinfold electron per site on a square lattice?
I think like if this is like a good description of the Hubbard model, you shouldn't need to add any other terms to it. Other terms to the Hubbard model. So like maybe this isn't like a good sort of trial wave function for the Hubbard model, but it should be contained.
Okay. Thank you.
Okay, yeah, so now I want to talk about the confining instabilities of this theory. So, right. So we have the fermionic spinons, which are moving in π-flux, coupled to the physical electrons. And then the question are, what are the possible types of symmetry breaking that can happen that will break this gauge symmetry. So the first possibility is that B is gapped. So B is just 0, and then we have fermions coupled to an SE2 gauge field. And the physics of this is known. So dating back to some old work, which instead of the π-flux phase considered bosonic spinons, this sort of bosonic spinons described a transition between VBS and AFM order. And recently it's been shown that this theory, π-flux, is dual to the sort of CP1 theory, which leads to the Néel VBS transition. And so we can basically sort of take all of the physics which has been worked out there and consider it in this scenario. So I think before it was sort of conjectured or hoped that this theory could have a second order transition as a function of some parameter, but I think more recently the field has kind of come to the understanding that through like DMRG or bootstrap that this transition is likely weakly first order. But I guess so that just is what it is, and this is what's happening when B is gapped. But then the case that we're considering here is a case when B is condensed. And in this case, depending on the way B is condensed, we can have different order parameters. So what are the possible orders we can have? We just need to look at the different gauge invariant combinations or bilinears of B. So we could have some charge order. So we could imagine looking at the density of the chargons, and if this chargons has some spatial modulation, then this will be inherited by the electrons as a charge density wave. We could also have VBS or bond order corresponding to this combination of B's or current order on the bonds. And then we have finally this object, which is BB rather than B dagger B. So this is something which is charged 2, and this corresponds to the pairing, which will be inherited by the C fermions. And if we work in a low energy version of this theory, so if we expand about the 2 minima of the spin liquid band structure, then what we'll find is that the possible phases in the continuum theory will be D wave superconductivity, period 2 stripes in either the X or Y direction, or something called D density wave order. It's a little bit of a misleading name, but what this phase is a phase which breaks time reversal symmetry. So it has current which moves in a loop around each plaquette, but it doesn't actually modulate density like a charge density wave. So these are the possibilities. Yeah.
Just to be clear, I mean, now you're mentioning D wave superconductivity. So the assumption is you're at delta not equal to 0, right? Where delta is the whole density.
This is at half filling. Sorry.
But you have a mod insulator. So how do you get it to become a D wave superconductor?
I mean, like in this theory, right, we're not assuming like large U or anything. That this isn't like we're not keeping like the full degrees of freedom of the Hubbard model, I guess.
No. So maybe okay. So suppose the C filling is 0, so you only have your π-flux state described by HF.
Yeah.
The size are neutral degrees of freedom. How do you get a D wave superconductor?
Because B is charged.
But are you condensing B's?
Condensing B? Sorry.
Yeah, are you condensing B's?
Yes. So when this order parameter is condensed, that's when we have a D wave superconductor.
I see. Okay, you're condensing B's, but you're at 0 density for the C's.
Yeah.
Okay, I see.
So in this scenario, I guess like the C's would be gapped. We're at like half. Yeah. The C's would like either annihilate or add an electron like at the next available state. But this is all at 0 doping.
Right.
Sorry, why is there like maybe?
No, that's fine. Okay.
Okay. Okay. Yeah. So these are the possibilities. Yeah.
Sorry. Maybe you will explain this. I can't wait. So you're gonna tell us what are these symmetries? SO5B, SO5F, all that?
Yeah. So SO5B. So this isn't like a sort of symmetry of the original problem. It's a symmetry which shows up in the low energy theory. And it's a symmetry which relates sort of these. Well, I guess here it's not clear, but these 5 independent order parameters. So we have 5 because superconductivity is 2 real order parameters, and then CDWX, CDWY, and d-density wave order will be the orders which are related by this SO5B symmetry. I think this will be easier to see. I'm going to like explicitly discuss sort of the low energy theory, and I think it'll be more obvious then.
Okay.
Yeah. Okay, and so then you can imagine if R is some kind of like chemical potential term for the chargons, that right at the critical point, this is where we've conjectured that there could possibly be a deconfined quantum critical point where the emergent symmetry is described by SO5 in the fermionic sector relating the Néel and VBS order parameters, and SO5B in the bosonic sector. So this is really kind of just like a conjecture, like there's nothing saying it can't be there, but naively, if you just look at sort of the dimensions of the quartic terms and the potential for the chargon, naively we're going to see that sort of the higher terms would have naive dimension that it would just or could spoil this critical point. So whether this happens or not is sort of a question which goes beyond the analysis here. It requires maybe like a 1/n calculation, which is something that we're starting to work on, or maybe some more careful numerics, but it's something sort of that we conjecture, but we can't really comment on beyond our sort of mean field approach. Okay. And then sort of to see what happens more explicitly when B is condensed. So we can write down a Landau potential for the B's up to quartic order. So these are the quadratic terms. The first term is just density, and the second term reflects the fact that the chargons are moving in π-flux. And then up to quartic order, sorry, it's not up there. Yeah, up to quartic order, these are the allowed terms that we find. So we need the U term, which is density squared for stability. And then if we're restricting ourselves to only nearest neighbors, I should have said this is also restricting ourselves only to nearest neighbors for the quadratic term. We can have density terms like this. The delta here is just the pairing order parameter, which was described before. Qij is the bond order, VBS order parameter squared, and then the current order parameter squared is this last one. And so you can imagine basically moving between different phases as you tune these different coupling constants. But this is something like 7 different possible sort of things to tune, and this is a very large phase space to explore and see what's possible even on a computer. And so it'll be sort of easier to tell what's happening first if we work in the continuum theory first. So in the continuum theory, we want to expand B, the chargon field, around the 2 minima of the band structure. So in the lattice theory, this means that from the previous slide, we want to choose R such that the chemical potential is lying right near the bottom of the band. And when we do this, we can expand the chargon in this way with over the fields in either of the 2 valleys. And we can construct what the possible order parameters are in terms of the low energy degrees of freedom. And what we find are the advertised order parameters, which should rotate into each other under this SO5 symmetry. So we have a CDW in the X direction, CDW in the Y direction, this d-density wave state, which breaks time reversal symmetry and has current loop order, and then a D-wave superconductor. So these are all the possibilities. I don't know if this is like a good time to return to the question of the SO5 symmetry, or I don't know if it's clear now.
Well, may I ask, like, okay, I assume B will just
Yeah.
transform under SO5B, right? So can I just understand what that is? I mean, right, like low energy wise, at low energy limit, we have two minimums, so I can live with, okay, some extra subscript, and other than the four entries of the 2x2 matrix that is B. And I assume that SO5 just acts, in some way among all these.
Yeah. So I guess like the way to think is like each of these could be real or imaginary. So we have SO8 relating sort of the individual components of the B, but then once we account for U1 and SU2 spin, we're left with the SO5 subgroup.
I see. Okay, thank you.
Okay. And then we can ask what the continuum phases are. So, or I guess I said what the continuum phases are, but when do we have which phase? So it's pretty simple. The Landau potential for the B's in terms of these continuum order parameters. We have V1, V2, and V3, which can be mapped back to, or I guess like the lattice order parameters can be mapped to these under some constraint on the additional sort of terms which were allowed in the lattice model. And then we can just vary them. And what we find is that when V1 is smaller than V2 and V3, this is when we have striped charge density wave order with period 2 in either the X or Y direction. Phase C is the d-density wave order with current loop order is shown like this. And then phase B is a D-wave superconductor, which happens basically when V3 is less than V1, V2. So whichever of the couplings is the smallest, so long as B is condensed, tells you which phase you'll end up in the low energy theory. But then to get a more sort of general sense of what's possible, we can move away from the continuum limit and go back to this lattice action and just choose an R such that we're no longer at the bottom of the band. And what's shown here is basically a representative example of what we found by varying all of these parameters as much as we could. So these are sort of what's possible to our understanding. So phase A1 is a stripe state where now lattice effects will pin the state to either be only along X or only along Y. Phase A2 is a charge density wave where in addition to ordering at 0 pi or pi 0, we also have ordering at pi pi. Phase E is a coexisting D-wave superconductor plus charge density wave ordering at pi pi, and then phase D, charge density wave ordering at pi pi plus D density wave as well, coexisting. And then C is still just the D density wave, and B is still D-wave superconductivity. Okay, and then just to basically show that we could get period 4 stripes out of this model if we added sort of the right couplings. It's a little bit artificial in that we had to go out to like next to next nearest neighbors to stabilize these, but eventually we can find some period 4 stripe states. So here the arrows are showing that there is some d-density wave, some current order, which is coexisting with the charge density wave. And this phase F is a bond-centered charge density wave where it seems like the density is peaking on the bonds. We can also find site-centered charge density waves also with period 4. And then phase H is basically phase G without any current density order. So this would just be a pure period 4 charge density wave. Yeah, and something that we're sort of interested in, I'll say, in this context, but haven't fully worked out, is sort of the Fermi surfaces these different possibilities would lead to. In terms of maybe matching more experimental, like quantum oscillation data or something like that. We could also consider adding more hoppings. The effect of this will basically be to increase the number of minima we can expand about for continuum theory. So in addition to W1, we could also add a W2, which is next nearest neighbor hopping, or even next to next nearest neighbor hopping, and we could keep doing this, but just to give a sense of how this might kind of change things or lead to new phases. If we choose a case where the next nearest neighbor hopping is positive and small, then the degeneracy or the doubly degenerate minima of the band structure will turn into degenerate rings. And then adding a smaller next nearest neighbor hopping will split the rings into 4 minima, so there will be 8 total. And then the reason why this might be interesting is now if we expand about the new minima, we find that the new continuum theory, in addition to containing the previous phases I discussed before, can also contain pair density waves. So where the pairing has some spatial modulation and coexists with a charge density wave. Okay, so to sort of recap what's the sort of full theory is, we have the spinons, which are moving in π-flux. We have the bosonic chargon sector, and the chargons coupled to the physical electrons. And now we can consider integrating out the electrons and then having a full theory which can describe both the B equals 0 and B as condensed phases. So far I've talked only about charge neutrality, but you could ask what happens if you were at some finite doping, or even if you were at 0 doping and it had some particle hole asymmetric band structure. So maybe if you added, say, like next nearest neighbor hoppings or something to the electrons, you would find that you would induce a term like this, in addition to like the double time derivative d tau squared b term. And this, in addition to the quartic terms previously mentioned and the potential for B, all naively should be relevant at the fixed point. So sort of the consideration in terms of the fixed point that we say might exist is the fate of all of these terms, whether their scaling dimensions could be modified when we take interactions into account but beyond mean field. But this is something that we sort of can't really comment on, but are thinking about now.
May I ask something simple here? I try to understand one of the things that you talked about. So if I just stay at charge neutrality and condense B, right? So there's nothing interesting about the chargon sector, but the spinon, does they stay gapless? Because you start off with the Dirac cone, right? And then there's nothing there seem to generate a mass for those stuff.
This is at, sorry, you're asking at half filling or
at half filling, when I just condense B, so I get some U-wave superconductor, I suppose. That's one thing that you mentioned. But it looks like in that superconductor, I still have gapless spinon. Is that right?
Yeah.
Wait, with the condensed boson, the gapless will be bosons. Yeah, of the D-wave superconductor.
Okay, you can say that. That's true. All right.
Okay.
No, it's the rock.
So that's it's the D-wave superconductor.
Those
are the
I see.
Okay. So to give sort of the high level picture, we have this theory of the π-flux spin liquid. What we've considered in our work is confinement transitions which can lead to D-wave superconductivity or charge density wave. I haven't talked about a transition where the physical electrons would have something like Néel order. This is something that's described in this other work done by another student in our group. They didn't consider the π-flux spin liquid, but they considered a theory of bosonic spinons coupled to a U1 gauge field, which is thought to be dual to our π-flux spin liquid. And in their theory, they're able to get different types of spin density waves and also Néel order. And then there's the other thing that maybe we would like to explain, which is a transition from the pseudogap phase into maybe strange metal phase. This is something that Suvir and Yahui have a paper from a few years ago, but it's sort of beyond the scope of what I'm talking about today. So to sort of summarize, we proposed a model of the pseudogap phase which we say can successfully capture some of the key aspects of phases seen in experiment. So one of these is a small Fermi surface in the pseudogap phase. We've also shown that we can get stripe states, d-wave superconductivity, and d-density order. So this is in contrast to past theories, which considered different spin liquids, which found d-wave superconductivity and d-density wave order, but no stripe state. And then we've conjectured that there's a possible critical point relating all of these orders and also antiferromagnetism and VVS. This is something that we're interested in, but it's hard to say what its fate will be sort of in the full interacting theory. And some other thing which is interesting to us is, so some previous work, so for example, this work by Assad et al. Considered the half-filled Hubbard model with an additional sort of kinetic term squared, and what they found in that model is a transition between antiferromagnetism and d-wave superconductivity. So we're interested in sort of relooking at models like this or this model and see if we can say anything either in some maybe quantum Monte Carlo or DMRG numerics about whether this could be related to the critical point we're proposing here. And with that, I'll conclude and say thank you for your attention.
Does anyone other than Xiaoming or myself has a question? Okay. Actually, on the last point when you said, I don't know this paper by Fucker, but did I get it right? You said this is a paper that found just conventional antiferromagnetism and d-wave superconductivity and some. That sounds very much like the old SO5 story. Due to some change.
Yeah. I guess so. I can't comment on whether it's sort of that better describes this particular paper, but yeah, this is like a completely different thing, because in our case, the antiferromagnetism is not related by the same SO5 symmetry to the superconductor.
I mean, I guess I should look at this paper. What did they do? Is it QMC or is it something?
It's QMC.
I see. Okay, thanks.
Yeah. I think, yeah, I'm not sure. I think in like kind of subsequent works, it looked like maybe the strength of like the strength of the d-wave superconductor was small, and they're not sure if it's like actually there anymore after all. But it's I guess like a little bit of an open question. Yeah.
Okay. Any other final questions for me? Okay. Well, if not, thank you very much for a great talk. Thank you.